Sorry, my overhead seems to be a little bit noisier today. Everything's a little bit noisier today. Here we have the graph with productivity being the y-axis and me and a better me, one assumes an even better me being the x-axis. With the little box being how productive I am, and the big box being how productive I'd be if I didn't have issues. And then there's the characters sitting there going, why am I doing this? Do I really want to be doing this? Why can't I just get this done? What am I doing? What's wrong with me? Welcome to Paralysis on Assignments. So this is chapter 7 of section 1. It's on dynamics, which is, energetic functions. And we're going to start out with dynamic equilibrium. Equilibrium, equal. What's equal in this case? In this case, it is a reaction. A reaction hits a point where its production in one direction equals the reversal of production back to the original reactants or the original substrates. So you hit a point where a lot of times, most of the times, the reaction trends in one direction. It tends toward making products. But if you build the products up to a certain point, they will start to undo what you just did. And the more you build them up, the more of them are undoing what you just did until what's producing them is now being equaled by what's unproducing them. That's dynamic equilibrium. Almost always lots and lots of products. Now I should mention that there's a lot of different ways to write down reaction rates. Sometimes, even in the same discussion, there'll be two different terms, two different letters that are representing reaction rates. K represents reaction rates, Q represents reaction rates, V, which very often is pronounced as velocity or presented as velocity, is reaction rates. There's a bunch more. And how stable are the products you're making? If the products themselves are pretty unstable, then the reaction might start coming back really, really quickly. And in some cases, that's okay, because you're not going to let the products hang around. You're going to scarf them up and move them somewhere. You're going to change them into something else. So even a reaction that hits equilibrium very quickly, you can keep going inside a system if you don't let the products build up. Enzymes in cells catalyze reactions. They catalyze reactions in a particular direction. They take a reaction that is very unlikely to happen, and they help it. They don't help the reversal of the reaction. So you can push a rate forward, and the equilibrium point it shifts a little bit. If you were just doing them in a test tube, the equilibrium point would be very different than if you were exposing the original reactants to a catalyst, something that pushes them in one direction. But that doesn't mean that at some point the products are not going to build up to a point of reversal unless, again, you're doing something about that. Going to throw a couple of things up here and then talk about them. You want to keep the reaction going? Keep throwing reactants in there. Is it keep building up and building up and building up, and you will eventually hit the equilibrium point. But your reaction can only go as quickly in the starting direction as it has stuff to react with. And so sometimes what affects not just the equilibrium, but how the reaction runs at all is, well, how much raw material are we giving it? How many reactants do we have? And if you're combining 3 reactants, whatever you have the least of is going to limit the reaction, right? If you're making cookies and you realize, okay, I'm way lower on brown sugar than I thought I was, then that amount of brown sugar limits how many cookies you're going to be able to make unless you want to change the recipe. And of course, in a reaction, you can't change the recipe. So that brown sugar becomes the limiting factor. It limits just how much you can make. And as I mentioned before, if you take the product and in cells you have chambers and movement systems and all sorts of things, you can move the product away from where the reaction is happening, either by physically moving it or by chemically changing it. Now, if you've got a sequence of reactions where you start at one end and you wind up with a product at the other end, you do eventually hit a dynamic equilibrium where all of the steps have hit their reversal equilibrium points, and then the whole system is in dynamic equilibrium. Think about that for a second. It makes sense, but it's not the easiest thing to grasp. Here's something I'm assuming you already know about. In order to get the reaction started, oh, you don't know about this because you can't see it. In order to get the reaction started, sorry, you need to get the reaction started. That takes a certain amount of energy. Sometimes it's just a matter of the reaction being warm enough that the particles are moving fast enough that they're hitting each other and enough times in the right angles in order to do what you want them to do. So heat is one of the big suppliers of activation energy. You cool down a reaction, the reaction cools, it slows down. Associated with that is a term called the Q10. And that is how much faster does the reaction rate get if we make the temperature 10 degrees warmer Celsius. And usually for an awful lot of reactions, you make them 10 degrees warmer, they go roughly twice as fast. This varies a lot, but rule of thumb is very often, if you want to double the rate of the reaction, make it 10 degrees warmer. When we talk about where life came from originally, people are now starting to think about the fact that it was a lot toastier in the originating oceans. And so a lot of the chemistry that people have been fiddling with, they need to think about it in terms of Q10s and Q10s for warmer circumstances. Some reactions, once you get them rolling, the products have a lot less energy than the reactants do, so energy comes out of the system. And if enough energy comes out of the system to actually supply more activation energy, keep the reaction rolling, it's an exergonic reaction. Set fire to a piece of paper. You don't have to keep setting fire to the paper in order for the paper to burn. The reaction of the breakdown of the carbohydrates releases enough heat to keep the paper burning. An endergonic reaction, the energy winds up being stored in the products. It goes in, doesn't come back out, or not enough of it comes back out. But for the most part, usually it winds up being stored and usually holding the products together. And so in order to get it rolling, you've got to keep putting energy into it. Photosynthesis is an endergonic reaction. Turn the lights off and the reaction shuts down, sort of. At least the beginning of the reaction shuts down. And in order to get stuff to happen in cells, very often this sort of reaction supplies energy to that sort of reaction. So you have an exergonic reaction and you're not really interested in perpetuating that, but you're interested in releasing energy to something that needs it. And very commonly, the energy is supplied by ATP. Adenosine triphosphate, where energy from ATP is supplied to here to change it. One of the phosphates comes off. I'm probably not showing you what I need to show you. I do that. Pointing with my shadow doesn't work. So this loses energy by a phosphate coming off of it. You get adenosine diphosphate. The energy is supplied to compound B. Now, one thing I don't like about this drawing is it ignores entropy and the fact that there's never 100% efficiency in an energy operation. Is that some of the energy is going to get frittered away as heat in the process. It's not going to be used in the product. So the energy level of compound B should be lower than the energy level of the starting ATP, because some of the energy transferred here is just frittered away as heat. So compound B should probably be somewhere lower, just in order for this to be right. But conceptually, that's something that's good to have in your head. Every transfer of energy loses some. It doesn't disappear, but it fritters out of the system as heat. Sometimes a lot of it does, and sometimes just a little of it does. But this is adenosine diphosphate, ATP. It's got adenine in it. It's got a nitrogen compound. It's got a sugar compound, and it's got 3 phosphates held on together by high energy bonds. Breaking of that bond releases a decent amount of energy that can be used to supply a system. Another thing we'll see is one of the ways that ATP can get something started is by actually taking one of these and sticking it on another compound. It's like, here, have a phosphate group. Well, the addition of the phosphate group to a larger compound can destabilize the hell out of it, make it vibrate and shake, and if you're trying to get it to do something, way easier to get it to do something if you've over-energized it. So it is a transfer of energy, but it's what they call a group transfer. And we will talk about that because we'll come back later and talk about how ATP works. See, again, they've got the energy lined up. Is that the energy really should come out at the lower level. Enzymes, organic catalysts. If you see The activation energy needed to supply, get a reaction started as a little hurdle to go over. Then what a catalyst does is it lowers the energy that it takes to get the reaction started. So the reaction happens more often, it happens more quickly, it happens more completely, driving it toward the products. In this case, this would be a reaction where the products have less energy than the reactants did, but not enough energy is released to drive them back over the hurdle. Enzymes are large molecules with dents in them, literally. And reactants fit into the dents. Those dents are called the active sites. The reactants then are called substrates because they're attached to something, they're sitting on something. And the presence of the substrates in the active site changes something about the enzyme. Very often it's conformation, changes its shape. And that stresses the reactants in some way, or may put a couple of reactants close together in a way that will greatly increase the chances that they're going to stick together. If you're building starches, you grab a sugar, grab another sugar, in the dent, they're right next to one another so that they can form the proper bond, alpha linkage, beta linkage. The dents would be different, depending on, you're positioning them, basically. Enzymes can have what's called a turnover number. Is that how quickly are the enzymes changing products to react, or substrates to products? What's the turnover? And in a cell, it can be in the thousands. And it can especially be enhanced by putting everything that you got to have working into a small room. Right? There's a lot of chambers inside a cell. Sometimes the reason for that is you've got a reaction that if it's, your reactants are spread through the whole cell, they're not going to find the enzymes that quickly, let alone find each other. But if you produce them in a small chamber, your reactants are in there, your enzymes are in there, your odds of everything coming together are greatly increased. So restricting escape, I guess. Enclosure is going to help. Okay, that's a good place to stop this particular. We'll get into Michaelis-Menten kinetics next.